Today we're going to be introducing organic chemistry. So organic chemistry is the study of carbon, specifically how carbon interacts with hydrogen, oxygen, or nitrogen, but there could be other elements in there as well. So some generalizations about organic compounds. They're mainly nonpolar. There's a reason for that. Their ENDs are very close to zero. In other words, carbon and hydrogen are like 2.2 and 2.4, so they're very close to each other. And so it's almost zero, and the molecules tend to be symmetrical. Now that doesn't mean there can't be polar organic molecules. As a matter of fact, there is a whole bunch of them, but in general, we say hydrocarbons or organic compounds tend to be nonpolar. They are soluble in other nonpolar solvents like oil. That's our like dissolves like saying, which we will learn about a little bit later in the year. And they are non-electrolytes. In other words, they do not conduct electricity when dissolved in water, except for organic acids. Again, we'll learn more about that when we get to our acid unit. And they have low melting points. Now, to review carbon, even though we shouldn't really have to, but carbon has 4 valence electrons. Therefore, it makes 4 bonds to satisfy the octet rule. And it is a tetrahedral shape when it does that, although when they get bigger than a single atom, then they're not tetrahedral anymore, and we don't really learn the names of their shapes at that point. There are 3 ways to draw organic compounds. You can draw them as a molecular formula, which shows just the elements and how many of them there are, like C3H8 is an example. You can do the structural formula, which has the full structure drawn to the octet rule. In other words, everybody wants to have 8 valence electrons except for hydrogen or the regular exceptions. So it would look like this. Ignore the 1, 2, 3. That's actually for the next one. Or you could do the condensed formula, which is much more common. And so the way that works is you number the carbons left to right, so carbon 1, carbon 2, carbon 3, and then you condense the hydrogen that are attached to it. And it can be actually other things can be condensed other than hydrogen, but at this level we almost never do that. So for example, carbon 1 has 3 H's directly connected, so I say CH3. Carbon 2 has 2 H's directly connected, so CH2, and carbon 3, again, 3 H's, so CH3. Now, it'll never be written like this with the 1, 2, 3 in red. It would just be drawn like this, CH3, CH2, CH3, and then you would be expected to uncondense it and understand that this would be the structure and that this could be the molecular. Now, the next thing we're going to do is what's called hydrocarbons. So for hydrocarbons, they are just H and C only. There's nothing else in them. Otherwise, they wouldn't be called a hydrocarbon. There are 3 types. There's the alkanes, the alkenes, and the alkynes. And depending on their last name, it tells you how many bonds are in them. If you can guess from the picture, an alkane means that the carbon-carbon bonds are singles. In an alkene, the carbon-to-carbon bonds are doubles. At least one of them are doubles. And in an alkyne, at least one carbon-to-carbon bond is a triple. Notice I'm saying at least one, because one double bond makes an alkane, and one triple bond makes an alkane, an alkyne, depending on, it doesn't matter how large the molecule is. As soon as you have one double or one triple, it fits into those categories. Now, this information actually is on page 7 of your reference table. It's right down here. So you've got your ane, your ene, your yne. Those are the endings. Ignore the 2 things in the middle. We'll get back to them. And then you've got the structures here. And if you look at the name and the structure, you should be able to figure it out. Ane, single bond, ene, double bond, yne, triple bond. And it's that simple. All right, next we're going to talk about the general formulas and how to use them. So the name for table Q in your reference table is called the homologous series of hydrocarbons. So you're going to highlight that. All right, that's an important name, not because the name itself has any real significance, but because a lot of times what you'll hear is on like a Regents, they will reference table Q. Instead of saying according to table Q, they'll say according to the homologous series of hydrocarbons, and then you'll have students be like, the what now? And they don't realize that that's the name of the table Q. So it is right here as well. It's highlighted. So be careful. They like to play word games with that, where they'll reference this by name, whereas all the other tables they'll just say, you know, table G, table F, table P. Like they'll just reference the table number. That one, I don't know why, but they love to spell the name out. And then it says at the bottom on table Q in blue, N represents the number of carbons. I have it written here as well. I can highlight that in blue here, where N is the number of carbons. And the N is for the formula. So your general formula for the alkanes, so these guys are alkanes. So the general formulas are right there. They're also found on table Q, listed in order, right? So for C3, N is the number of carbons. So that would mean that I would have 3 carbons, so it would be C3. And then I would just make N3 and do the math. 2 times 3 plus 2, I end up getting H8. That's my general formula for an alkane with 3 carbons. If it were a alkene with 3 carbons, then it would be C3H6, because 3 there, and then 2 times 3 makes 6. And if it was an alkyne with that amount, it would be C3H4. So there's your alkenes and alkynes. I'll do a few more. And if you notice the pattern, once you have the alkane, you just take 2 away for the alkene, because again, that's how you gain the double bond. You lose 2 hydrogen. And then for the alkyne, you just take 2 more hydrogen away and you gain the triple bond in its place. And so that's what's happening. They lose 2 each time you go down. So I'm just doing the math in my head, but you get the idea. Now, a alkane is considered a saturated hydrocarbon. So what that means is it has the maximum number of single bonds. That's why it's an alkane. You've probably heard the word saturated in terms of saturated fat. Well, that's exactly what a saturated fat is. It's a fat molecule that has all single bonds, whereas an unsaturated fat has less than the maximum number of bonds. That's a fancy way of saying that it has a double or triple bond. That's literally all that means, all right? So now we're gonna get to naming. So in order to do naming, I'm actually going to pick naming up on the next video, because I want to go right into the next page and do the names that way. In this video, we're going to learn how to name the most basic hydrocarbons, and then there'll be a follow-up video where we name more advanced ones, several follow-up videos where we name more advanced ones, but today we're just going to focus on the easy ones. So a couple things. If there's a double or triple bond, the carbon chain must be numbered, kind of like a condensed version that I showed you before, if more than one version is possible. I'll explain what that means when we get to it. It's actually much easier to do or to see once we get to a problem that can do that. And then you number the carbon chain so that the double or triple bond is as low as possible. Again, I'm going to explain that when we get to it. So let's just start with the naming and go right into it, and then we'll come to those when we get to our second set of problems. So for naming alkanes, so these guys have all single bonds, so that this makes the naming very easy. If your formula says there's 2 C's, you're going to write out your general formula, C2H6, C4H10, C5H12, C6H14, and C6H18. Now we're going to draw their structure. I'll come back to the name in a second. So we need a stable structure. So here's the easy way to do it. Since they're all single bonds, you bond your 2 carbons together. Here, you always start by bonding your 4 carbons. And this one has 8. So now we are going to add our H's. There's my 6 H's. Every carbon has 4 bonds, which is what I'm looking for. So 1, 2, 3, 4, 1, 2, 3, 4. The bond that's shared gets counted obviously towards both. So every carbon has 4 bonds. All the hydrogen have 1 carbon. I've got a stable molecule. That's how you check them. So the next one, four carbons, 10 hydrogen, all the carbons have 4 bonds, all the hydrogens have 1 bond. Again, that's how we double check. As you can see, they get larger. I want you to draw the H's every single time. I do not want to see this. While I may do this in class, you are not allowed to. Not yet. Common mistake I see a lot is I'll see students writing lowercase h's. I don't know if it's just because lowercase h is easier to write, mildly easier to write than a capital H, but don't write lowercase because element symbols are always capitalized. So if you write a lowercase h, then it does not mean hydrogen in terms of chemistry. It means something else. What it means, I don't really know, but it definitely means it's wrong. I can tell you that much. So there's your structures. Now let's name them. So the way we name them is we use table P and table Q. 2 carbons in a row, there's a prefix for that. Now normally in naming, we would use, mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. We use those for naming covalent compounds. Well, here's the unfortunate part. Organic compounds get their own set of prefixes. Luckily, most of them are the same, but the first 4 are not, meaning for naming covalent, pent, hex, hept, oct, non, dec are the same, but the new ones are going to be meth, eth, prop, and bute. So you may want to write that in. For covalent molecules, we use mono, di, tri, and tetra. For organic molecules, we use meth, eth, prop, and bute. All right, so you get your prefix from here. So 2 carbons is eth. And then the ending, since it's an alkane, it gets an ane ending. So it becomes ethane. The eth tells me that it's 2 carbons. The ane tells me that it has all single bonds. For the next one, it has 4 carbons. So bute. ane ending tells me they're all single. So butane, maybe you've heard of it. You've probably heard of propane, which is what we burn if you have like a gas barbecue. You burn propane for that. Same, and then a lighter, like the little lighters that you use that have the liquid in it, that's a butane lighter. That's because it's burning butane. So they are around and they are, very common fuels. But let's finish the rest. So we have pentane. This one would be hexane. You can make it a capital or a lowercase. I don't really care about that. And for this last one, octane. Maybe you've heard of that when you buy gasoline. If you drive a car yet, when you buy gas, there's numbers at the pump. Usually they're like 87, 89, and like 93 or something like that. If you read those little labels, like under it, it says it's the octane rating. It's how much octane. It's actually in what's called parts per million, which we'll learn about later, but it is the rating of how much of the octane is in that gasoline. The higher the octane, the more expensive, and typically the better the gas is. So, condensed formulas. So these should be pretty easy. Carbon 1 would be right here. Maybe I'll use a different color to make it stand out. So there's carbon 1. CH3, there's carbon 2. CH3. So if you notice, there's going to be a very obvious pattern here. CH3, CH2, CH2, CH3. The next one, I'm going to go a little faster. So the way I count them is I've got 1, 2, 3 carbons in the middle, so I have 3 CH2s, and then a CH3 on either end. There we go. And then the last one, I'm probably going to run off the page, so You can totally do that. That's fine. There is a faster way to do this, but again, you don't get to do it until you've graduated. This means the same thing as that. It's basically saying I just take the CH2 and repeat it 6 times in a row, and then I end with the CH3. You don't get to write that on the Regents ever. So a common question at the end is how many bonds are in a molecule of propane? So propane, if we know, propane, the prefix means 3. So the common answer that I see a lot is 3, and you get it wrong. Another common answer is to say, well, propane is C3H8. So if I just add 8 and 3 together, I'll get 11 bonds. And then you also get it wrong. The only way to really do this is to draw the propane out and then count the number of bonds. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 bonds in a molecule of propane. So be aware of that. They like to put that, I like those questions, or I should say those questions do show up a lot. It's kind of silly, but they're easy points, so that's why I like them, as long as you don't fall into the trap. And typically it'll be a multiple choice question, and you'll see like choice A will be 3, choice B will be 11, choice C will be some random number that makes no sense, and then choice D will be the actual answer, or it might be a part 2 as well, because then they could say I want to see it as well. So just be aware of that. Now let's get to the harder ones. So alkenes are where some of these rules that I skipped over, those rules that I said that we were going to skip and come in when I got to it, well, now we're here. So alkenes have those weird rules where we may have to number the carbons, and we're going to have to count the double bonds. So I'm going to end this video here and then pick up the alkene video in a separate section. We're going to be talking about how to name alkenes and alkynes. In my previous video, we did alkanes. They're pretty easy. We're going to do alkenes, and specifically we're going to focus on when to use the numbers. So I mentioned it when I did the alkane video, and I said sometimes we're going to have to include numbers in the name when there's more than one variation. For an alkane, that doesn't really happen ever, except for when they're branch chain alkanes. In an alkene, that'll happen when the atoms get more than 4 carbons in length, or 4 carbons or more in length. You're going to need numbers. And I've got my model kits today, and I'm going to try to show you why we use numbers on some and why we don't use numbers on others. So let's start with drawing the structures. So the way I'm going to tell you to do these, the way I always start with them, is simple. Just do the carbons first. So this first one is 2 carbons, this next one is 3 carbons, and this final one is 4 carbons 3 times in a row, and there's a very specific reason I'm doing that. And note, if you notice, I don't have any double bonds in them. I'm just putting in single bonds between carbon. Now, the reason we're doing that is because we're going to add the double bond in after the fact. So for this first one, there's only 2 carbons, so the double bond has to go there. So when we draw this, it's 2 C's, and then it has 2 H's. So you can put your H's like this, like in your table, in your reference table, if you think it's Q. Table Q has it like this, or you could put them like this. Ultimately, it doesn't matter, okay? Just keep in mind, if you drew them like this and like this would still count as a symmetrical molecule. Because we don't really worry about the position of the H's, because in 3 dimensions they are in specific locations, and so that changes things a little bit. So there's my 2 carbons. The name, ene, no number. Condensed formula, CH2, CH2. Now, this one's easy. Let's go to the next one, and we'll start running into some issues. Some people will do this, and so I'm going to choose to put the double bond here. Some people may look at this and say, well, they put the double bond. I'll use this as an example. There. So then if we draw the molecule out, right, it's going to look like this. There's 2 H's on this one. There's going to be 1 H there. And then this molecule is going to look like this. And again, whether you put the H, this middle carbon gets the H up or down, doesn't matter. In real life, it's free to rotate around, so it is rotating. So that doesn't really matter. And so you would then say, well, what about these? These look different. So here's what I want to show you. This represents the first one. So if you look at it, this is the double bond here. This is the single bond. The balls are the carbons. And now what I did was I got rid of all the H's just so we could focus on the carbons, because that's all we have to really worry about now. And then the other way that I drew it would be this one, okay? And so here's the second one, and that's that. And so if you look at them, here's what's really going on. They may look different, but in 3 dimensions, look at what happens. They're no different. They're the exact same molecule. All I'm doing is taking one molecule, here's another angle, and I'm just drawing it like this. I haven't actually changed the molecule, I just rotated it, okay? That would be like saying, you know, this pen is somehow different from this pen because the point's in the other direction. It's the same molecule, it's the same pen, and it's the same thing here. If I drew it like this, all I would do is just take my molecule and rotate it. I'll put it up here, and that's the same molecule. There it is. Okay, and again, whether you drew this middle H up or down doesn't make a difference. It's free to rotate. Whether you drew these 2 H's on the right sideways in the bottom, or top and on the side, or on the angles, kind of like splitting the difference, it doesn't make a difference, because in real life they kind of move wherever they want to, and you don't really have control over that. So all we really care about when we're comparing molecules is how many carbons on this carbon, or how many H's on this carbon, how many H's on this one, how many H's on this one, and then the double bonds, how many of them there are and where are they. So these molecules are the same thing. So because of that, we're not going to change the name. This is just going to be propene. Done. It's that simple. Okay, there's no numbers, there's no variations. If you drew it this way or if you drew it this way, they would both be correct. Your condensed formulas would be different. Okay, this would be CH2, CH, CH3, and then this one would be but if you look, it's just the condensed formula backwards. It's CH2. Well, the start here, CH2. Well, this one is CH2, and then the middle one is CH in both cases, and then the far left and the far right are CH3. So it's just the reverse condensed formula, which is totally fine too, as long as it gets you the same molecule. Now, another question I get a lot is, well, if you were looking at the condensed formula, how would you know there's a double bond there? And the answer is, unfortunately, let's go to another page. The way you would figure that out is to uncondense it. So if you uncondense this, you'd say, okay, there's my first carbon, it has 2 H's. Then there's my second carbon, it has 1 H. Notice I didn't put a double bond in there because I don't know it's there. And then here's my third carbon, and it has 3 H's. And then you look at this and you say, hey, octet rule says all carbons want to have 4 bonds. This carbon has 4, 1, 2, 3, 4. But this carbon only has 3, and this carbon only has 3, so these 2 carbons are 1 bond short. Then you go back in and say, there must be a double bond there to make all the carbons have 4 bonds. So that's how you have to do it. You actually have to go in, find the area where you're missing a bond, and then put the double or triple bond in. So unfortunately, they don't spell it out for you. If you were given the name, it would be in the name. The ENE tells me there's a double bond there. And so that's one thing. But if you were just given the condensed and you had to draw the structure, you'd have to figure that out on your own. Now let's go to our favorite one, these guys. So there's 3 versions of butene. So these would all be called butene, and when you're doing these, the easiest way to do it is I like to start on the left, and I'm just going to put my double bond in there, and then move it 1 carbon over there, and then I move it 1 carbon over there. So now I've hit every version. All right, then we're going to number it. We're going to call this 1, 2, 3, 4 carbon 1, 2, 3, 4, and then this would be carbon 1, 2, 3, 4. And so if we name these, right, this is where we need a numbering system in the name, because we can't have all 3 of these be the exact same name. We need to differentiate between them. So I'm going to call this 1-butene because the double bond is between carbon 1 and 2. This would be called 2-butene. And if you thought this would be called 3-butene, you are wrong. It's actually 1-butene again. Okay, so I did this on intentional. The numbering is wrong. Okay, and here's the reason why. So here's my first butene. So it's 4 in a row. Double bond is between carbons 1 and 2. Put it right there. Here's my second butene. It's 4 in a row. The double bond is between carbons 2 and 3. And then here's my third butene. 4 in a row. The double bond is between carbons 3 and 4. So we thought. But I could just do this, and the first and the third are the exact same molecule. They're just backwards. So they're no different, which is why they don't get a different name. Whereas the middle one, no matter how I rotate it, right? No matter how I rotate this, the double bond is in the middle, and the double bond will never go on the ends just by physically manipulating the molecule. If I wanted to get the double bond at the end, I'd have to change the way the bonds are connected. Whereas with these two, all I have to do to make the double bond be on either end is just rotate the molecule. And if I rotate the molecule without disconnecting anything, well, that's not a different molecule. That doesn't count, okay? So that's all I have to do. I just have to rotate it, and now it's here. Rotate it again, and it's back to where it was. So what we would do, and this is what I'm trying to teach, is the numbering system. Here's the easiest way to do it. Since the double bond is closer to the right, I call this carbon 1, this carbon 2, this carbon 3, and that carbon 4. And then you can see there's two variations, all right? It's that simple. And so if there's more than one variation, you need to use a number to tell me where the double bond is. For ethene, it's too small. There's only one version, no number needed. For propene, it looks like there's two different versions, but you just flip it and it's the same molecule. When you get to 4 or more, now there are different versions, and the bigger you get, the more versions you have. So there's 1 butene, and then there's 2 butene. So a good way of figuring it out is this. If you were to draw a bunch of carbons in a row, so I'm just going to pick a random amount, 1, 2, 3, 4, 5, 6. If you were to put a line right through the middle of the molecule, then it turns out that's how many versions of the molecule there are. Meaning I could put the double bond here, here, and here, right in the middle, and then I get 3 different versions of this molecule. If I put the double bond here, well, it's just the flipped version of this one. And if I put it here, it's just the flipped version of this one. So you can go through, once you get the double bond, you can rotate it from carbon to the next carbon to the next. Once you hit the middle, you've done every version possible. So in this case, the middle would be right in the middle of this bond. So I put it here and here, and I've done every version. This one is just a flipped version of that one. Hopefully that makes a little bit of sense. The condensed formula is going to be, well, let's put the H's on. And so our condensed versions are going to be CH2, CH, CH2, CH3, and then this one would be CH2, CH, CH, CH3, and this final one, there's a missing an H here, so it's going to be CH2. And then the way to double check is make sure every carbon has 4 bonds. So when you look at this one, you say, all right, carbon 4 has 1, 2, 3, 4 bonds, carbon 3, 4, carbon 2, 1, 2, 3, 4, carbon 1, 1, 2, 3, 4. So as long as every carbon has 4 bonds, you did it right. Last question on the bottom is how many bonds are in a molecule of propene? This one tends to throw people off. Again, anytime you do this, I always recommend drawing it. The common mistake is to say prop 3 bonds. So if we look at it, propene looks like this. It has a double bond, which means it's going to not have as many hydrogen as an alkane. So a common mistake is to say, okay, C3H6. Well, if I add 6 and 3 together, I get 9. And then you say, well, there's 9 bonds in it. That might be right, might be wrong. The smart way to do it is to draw it and count it. So in this case, it's 1, 2, 3, 4, 5, 6, 7, 8, 9. So you get lucky it's 9 bonds. With an alkane, it won't necessarily work out to be that. You can't just do that. And with an alkene, I don't think it works out as well either. So be aware of that. Always draw those out. And that's it for the alkene video. I'm going to pick up with the alkyne in their own video. In this video, we're going to do alkynes. So I put the general formulas in just to save a little bit of time. When we draw these out, again, I always like to connect them with a single bond to start, and then we'll add our triple in after the fact. So for the first one, the triple bond doesn't have anywhere to go. It goes there. For the second one, you could put it here or here, because again, just like I did in the last, I mentioned this in the last video with more detail on the models. If I put it here or here, it's the same thing. You just flip the molecule and these are the same spaces. Now, when you get to 4 or more, now you have some variation. So the way you do that is I always like to think of it like this. So I'm going to put a red line, dotted red line here very lightly. And I'm going to say, all right, I'm going to put double bonds, or triple bonds in this case, in the molecule starting at carbon 1. And then I'm going to move it 1 to the right. And then I'm going to move it 1 to the right again. And once I've hit the middle of the molecule, whether that be a bond or an actual carbon, and depending on if it has an odd number or even number, it doesn't make a difference. But once I hit the middle, I have done every version of that molecule that is possible. Because if I moved it here, it is just a mirror image of this one. And if I move it here, it's a mirror image of the first one. So that's why once you hit the middle point, you've done every version. All right, now we need to number them. We don't number the first one because it doesn't matter if I call this carbon 1 or this carbon 1. If I flip it, it's the same thing. So this is just ethine, okay? And then the next one is going to be propyne, okay? And again, whether I call it carbon 1, 2, or 3, or if I tried to number it, if I put the triple bond here, I would just call it 1, 2, 3. I would just number it in the reverse order. It would be 1 either way. Since there's no such thing as 2-ethine and there's no such thing as 2-propyne, then I don't need a number. So a good way to explain this is like house addresses. The reason you need a house number for your house is because there's more than one house on your street. If you were like super rich and you had your own street and you were the only house on the street, turns out you wouldn't need a house number. You would just say, so let's say I win the lottery and I buy my house in the middle of nowhere and I have my own street and I call it Castle Learning Avenue. If I was the only house on Castle Learning Avenue, I don't need a house number. I just say, I would tell the mailman, deliver it to Castle Learning Avenue. Well, what house? The only house. There's no number needed. Well, as soon as I get a neighbor, so let's say a neighbor came and they were like, all right, I'm going to move next to you on Castle Learning Avenue just because they like Castle Learning so much. We would now need house numbers because the mailman wouldn't be able to say, okay, well, which house does this particular mail go to? Do I go to number 1 or do I go to number 2? And that's where these numbers come in. If there's more than one version, then it needs a number. If there's only one version, then you don't need the number. It's not necessary. There's only one version, and that's how it works. So I'm going to add the H's in to save time. I am just going to write lines to represent H's. Okay, so for these first two, let's condense them. CH, CH, and then this one would be CH, just a C, then another C with 3 H's. Hopefully everybody understood that last part. And then for these, we'll add our H's in as well. Put an H there, nothing on that carbon, and then it's back to normal. And then for this one, 3, nothing, nothing, 2, 2, 3, 3, 2, nothing, nothing, 2, 3. So for this, it is going to, when we do our condensed, it is going to look like this. CH, that's this carbon. And then for the next carbon, it's just going to be a C. And then for the following carbon, it'll be CH2, 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 CH3. And then for this one, we've got CH3 for this first carbon. This second carbon doesn't have any H's, so we just write a C. The third carbon also doesn't have any H's, so we write another C again. The fourth carbon, CH2, CH2, CH3. And then for the last one, CH3, CH2, C, C, CH2, CH3. And then for the names, these would all be hexyne. But they're going to need numbers to differentiate them between them. So this would be 1 hexyne, 2 hexyne, 3 hexyne. One of the things that hopefully will make this a little bit easier to understand is if you look at 1 and 2, those are polar molecules, because if you draw your symmetry, they're asymmetrical. When you get to 3, it's nonpolar, and because it's symmetrical. And so polar versus nonpolar means they have different intermolecular forces, and therefore they're going to have very different boiling points. And so 1 and 2 will be very similar, it turns out, but 3 will be very different in terms of some of its properties. And so you do have to, that's part of the reason why they need different names, because they do have different properties, because they are not the exact same structure. Their properties are often very similar, but they are different enough for us to worry about, which is why we have to come up with different names for them. And then the last one, how many bonds are in a molecule of propyne? Draw it out. So it looks like that. So if I count my bonds, 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 bonds in a molecule of propyne. The formula would be C3H7. So if you were to just add up 3 and 7, you'd get 10. It wouldn't work. If you try to say prop is 3 carbons, so there must be 3 bonds, that's a common mistake a lot. So you'll see a lot of that. The best way to do it is to just draw it out and then count the number of bonds. And that's everything for alkynes. In this video, we're going to learn how to draw branch chain hydrocarbons. So the first thing I want to mention is that these guys are typically what we would call isomers. So an isomer is when you have the same formula but a different structure, which causes different properties. So an example of an isomer is C4H10. It could be this one, or it can be this one. Both structures are valid. They have different properties. For example, one is symmetrical and therefore nonpolar, and the other is asymmetrical and therefore polar. And so just by changing the shape of the molecule, you're going to change the properties of the molecule. That's where the term isomer comes from. Don't confuse it with isotope, and don't confuse it with allotrope. So they are different. They sound similar, but they are not the same. Allotrope is actually very similar because it's when you have an element with the same formula, but a different structure and therefore different properties, whereas an isomer is when you have a compound that has different structures and different properties. So that's that part. What we're going to do is learn how to name this giant looking thing. Okay, so let's start. Here's the rules for naming. They're right here at the bottom. It says, first, find and name the longest continuous chain. If there's a double bond or triple bond, it must be included. So here's what that means. So I'm going to highlight that here. So the longest continuous chain, so there's this guy. So now, here's my question. Once I get to this point, I have a choice. Do I go up 2 more, and then the longest chain would be 1, 2, 3, 4, 5, 6 carbons long, or do I go to the left, and then I can go further? Can I get longer than 6 in a row if I go left? And the answer is, I can definitely get longer than 6 in a row if I go left, because now I've gone 1, 2, 3, 4, 5, and I could go 6, 7, that's 7 in a row, or I could keep going 6, 7, 8. Well, I'm definitely going to keep going. And now the last question is, do I go down or do I keep going? And so I keep going, and then is that the longest continuous chain? And the answer is no, it's not. The longest continuous chain would mean there. So the way you figure it out is you've got to find the longest linkage of carbons in a row in the molecule, and you can't double back. So you can make a turn, okay, but you can't go backwards. You can't go back on a carbon you've already counted. So in other words, I could have went 1, 2, 3, 4, 5, 6. I could go 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8. Or 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's the longest possible chain in the molecule without doubling back. Okay, so that's step 1. And then we can actually name that. So I'm going to put the name here. If it were a 9 in a row is a non. And then because it has a double bond, it's a non-ene. Okay? Now, step 2, it says number the chain to have the lowest possible side group numbers. The double triple bond gets priority. So what that means is, since this double bond is closest to the left, I'm going to start numbering, on the right. I'm going to start numbering on the right. So I'm going to call this carbon 1, carbon 2, carbon 3, 4, 5, 6, 7, 8, 9. The fact that this is bent up means nothing. It could very easily be straight, and then this, which is this blank one, which is a hydrogen, would be in its place, and you could have drawn it straight. The only reason they put a bend in it was to see if you could identify the longest chain and make it a little bit harder for you to do that. So since the double bond is on carbon 2, we're going to call it 2 non-ene. Next part, step 3. Name each side group before the main chain. So we've got some side groups. Or they're also called branches, but same idea. So think this is like a tree, and these are the branches. There's a branch of 2, there's a branch of 2, and there's a branch of 1. So for a branch of 2, notice the branch gets a YL ending. So what that means is, normally we would write this out as 2 carbons in a row would be F. Because it's a branch, it ends in YL. So this would be 4 ethyl. And then this would be 5 ethyl. And then this would be 7 methyl. The reason these are called ethyls is because the branch is 2 carbons in length. It's called 4-ethyl because it's on carbon 4. Whether it be up or down does not make a difference. In real life, they're free to rotate around the molecule in 3 dimensions, so it doesn't matter. Same thing with carbon 5. It's 5-ethyl because it's too long. And again, you could draw it up or down. It wouldn't make a difference because, again, free to rotate. And then this is 7-methyl. Now, what you would do is you would normally put those all together, but that name wouldn't be 100% right either. So I'm going to show you where the mistake is. Normally, you would write it out like this. You would write 7-methyl, 4-ethyl, 5-ethyl, 2 non-ene. But there's a couple things. There's a couple reasons this is wrong. One, technically, the branches are supposed to be in alphabetical order, so the ethyls should come first and then the methyl goes second, so that's one thing. But 2, we can condense these 2 down to this. 4, 5 di-ethyl. Now the reason it gets the di is because if the same group shows up more than once, we can condense them down. Now, again, I know some people might be thinking, why bother to give it an extra name? The fact that there's 2 numbers means that you shouldn't need to tell me that there's 2 ethyls. The 2 numbers tells me that there's 2 ethyls. While I agree with you, that's just not how it's done. And so then that would be this part. And then the next part would be 7-methyl 2 non-ene. And that's the full name. All right. So that's how you name hydrocarbons. This one was a harder one. I wanted to start with a hard one. The next thing we're going to do is we're going to condense it. So the way I'm going to condense it to make things easy is I'm just going to condense it from left to right the way we read. I just find that much easier to do. So I'm essentially condensing it backwards. So carbon 9 has 3 hydrogen. Carbon 8 has 2 hydrogen. Now watch how I do this. Carbon 7 has 1 hydrogen directly, meaning this is a hydrogen, right? They don't write, at this point we're not writing the H's in. So there's your 1 hydrogen. But then it has a CH3 on it connected to the other side, so parentheses CH3. The parentheses tell me it's connected to the atom or the carbon behind it. Carbon 6, CH2, carbon 5 is CH, and then parentheses, now I condense this one. This first carbon in the chain is a CH2, the second carbon in the chain is a CH3. Now I'm back to carbon 4, C with an H, and then parentheses, CH2, CH3. Then carbon 3 is just a C with one H, carbon 2, a C with one H, and carbon 1, CH3. Now, some people usually ask this question. They say, well, how do I know that there's a double bond there? And the answer is, if you were to uncondense this, you would realize that there would be one bond. These two carbons, carbons 2 and 3, would be one bond short. They would be one hydrogen short of being stable. And so the only thing you can do as a result is bond them together to make a double bond. So you have to be able to figure that out when you look at that. You say, oh, it's missing carbons or missing hydrogen, so I'm going to have to double or triple the bonding in order to make it stable. So that is how branch chain hydrocarbons work. Let's do one more practice problem. Let me find it. So now we're going to do this one. And that's it for branch chain. We're going to do a bunch of practice. So again, first step, find the longest chain. It's got to have the triple bond in it. So you could go 1, 2, 3, 4, or you could go 1, 2, 3, 4. It actually wouldn't matter. So it wouldn't matter if I went this way and to the left, or if I went straight across to the left. The reason being, if I number this 1, 2, 3, then on carbon 3 there's a branch 2, and if I did it the other way, it would be 1, 2, 3, and then there'd be a branch of 2 on carbon 3. So it doesn't matter. The name's going to be the same either way. And now here I'm going to go to this carbon, and now the question is, do I go up 1, 2, do I go down 1, or do I keep going across? Well, turns out if I keep going, I can get more carbons in. Now the question when I get to here, do I go up and end it? Do I go down and end it? Or do I keep going straight across? And straight across is the longest one. Since the triple bond is closer to the right, 1, 2, 3, 4. Because if I numbered it the other way, it would be 1, 2, 3, 4, 5. Yeah. So by doing it this way, the triple bond is between carbons 4 and 5. If I did it the other way, it would be between carbons 5 and 6. So there's my 9 carbons. That makes it a non-ine, and specifically 4 non-ine. Now some people ask, why 4, not 5? We always use the lower number. So since it's between carbons 4 and 5, we just call it 4. If it was between carbons 3 and 4, then it would be called 3. All right, now we do our branches. Well, turns out branch of 2, branch of 2. I'm going to use a different color. Branch of 1, branch of 1, branch of 1. So let's combine these branches. So this would be 6 methyl, 7 methyl, 7 methyl. Notice this does not count as a branch of 2 because I have 1 down and 1 up. That's 2 individual branches of 1. So that's why I have 7 methyl written twice. That'll show up in the name. This one would be 6 ethyl, and this one would be 3 ethyl. So now let's combine it. The methyls, let's do the ethyls first because alphabetically E becomes before M. So the ethyls are going to be 3, 6 dash diethyl. Notice I'm using dashes to separate letters and numbers, commas to separate numbers from other numbers. And then for the methyls, it's going to be 6, 7, 7 dash trimethyl, and then I overshot a little, and then it would be 4 non-ine. So notice a couple things. There were 2 methyls on the 7, so the number 7 has to be written twice. If they happen to be on the same carbon, you still have to double that number up, because what it's saying is what this really means is trimethyl means there's 3 branches of 1. 6, 7, and 7 are where to find them. Diethyl means there are 2 branches of 2. 3 and 6 are where to find them. For non-ine says there's 9 carbons in a row. There's a triple bond between carbons 4 and 5. The 4 is where to find it. So that's what it means. And then the condensed structural is going to look like this. We're going to start with carbon 9, CH3, CH2. I just write a C because carbon 7 doesn't have any H's of its own. It only has branches. So I just write a C. Then I do a parentheses, CH3, close it, 2. So you can get away with this because the branches are the exact same, so you can put a 2 out. If you aren't comfortable doing that, then you could just write parentheses CH3, close the parentheses, a new parentheses, another CH3, close the parentheses. You'd have to write it twice. When you see carbon 6, hopefully it makes more sense. So there's carbon 6. There are no H's for carbon 6 either. So it doesn't matter which one I do first, I don't care. So parentheses, let's do the bottom one first. CH3, close it. That's for this one. Then I do another set of parentheses. CH2, CH3, that's this one. Again, close it. Now I'm on to carbon 5. Carbon 5 has no H's, so I just write a C. Carbon 4, no H's, so I just write another C. Carbon 3 has 1 H, and then in parentheses, CH2, CH3, that's this group, and then CH2, CH3 for carbons 2 and 1. So that's how you name hydrocarbons. These are very complicated hydrocarbons. Normally, the ones you're going to be doing in lab are not going to be this large that often. They're going to be much smaller and take a lot less time. But if you can understand this one, then the smaller ones should be no big deal because they should be pretty easy at this point.